That's our direct and indirect effects. Anyway, so let's keep going.
Yes, you do want to cut that.
Yes. So but it was just so funny. It's like that's the paper you're going to get upset about, not talking about parent, not the stuff that number crunching is going to annoy you. So we can, like I said, you can look at this and say, look, 50.6% of the effect is mediational. 49.4% is that direct effect. We can start to look at those direct and indirect effects. Now, keep in mind, it is model specific. If I add variables, those effects are going to change, and we'll see kind of later how that happens. What?
Look, it's small.
Yeah, because now we start to break it off and carve it up a little bit. So a few things I wanted to point out. Again, causality, I've implied a causal model, but as we said, you want to have it based on theory, temporal ordering, research, logic. I'll tell you kind of what's the sequence you should be doing. You have to have an association. If there's no correlation, no association, No. I'm thinking. Anyway, as the book points out, you must have an association. It's not quite that simple, but there does need to be an association, and you want to be careful for spurious relationships. Some jargon, and I'll just go through this quick. You got the slides, but things you want to make sure you understand the terms in case we use them. Recursive models and non-recursive models. We're going to focus on recursive models where causality only goes one way. You can have what are called non-recursive models where you have arrows going to both ways between the same variable, or little loops where A causes B, causes C, causes A, causes B. That's beyond this course. It's much more complicated. You need specialized software. And as Keith points out, it's often just an intellectual cop-out. People don't want to commit. You don't want to say this causes that. So it's like, I'm just going to say they're quad. No, think about it. Make a decision. Studies that have looked at it, he makes the point. Often when studies do go through the effort of looking at bidirectional effects, it really does seem to be it's really one way, not the other. So don't be a wimp. Take a stand. Look at the theory. Which causes which? Is it parenting causes behavior? Is it, think about it. Okay? Under-identified models, over, and just identified models. An under-identified model is where there's not enough information to estimate numbers. X plus Y equals 5. X and Y can be anything, so that's useless. Under-identified are completely useless in that sense. Nothing we can do with that. Just identified models, or there's exactly enough information to estimate. So if I say x plus y is 5 and x minus y is 1, what's x? What's y? 3 and 2. Right? 3 plus 2 is 5, 3 minus 2 is 1. So I can, and that's it. That's the only values. What we've done so far with multiple regression, notice we have three equations, 3 unknowns, we exactly solved. That's a just identified model. Then you can have over-identified models, where there's more information than you need to estimate the model. So I would do the same thing. X plus y is 5, x minus y is 1, x times y is 4. There is no answer for that. You can't solve that. Which makes you think, well, that's got to be useless too. No, this is actually beautiful. This is what we like. And the reason we like the over-identified models is because it lets you, you'll start to see, next week we'll start to see some of the benefits that lets you evaluate, well, how good of a model do you have? You can think of it this way. Let's say that I pick a value of x and y. I say x is something, and because there's no perfect answer, I can pick a number for x and a number for y. And these are going to be wildly off. My estimates are going to be nowhere near 5, 1, and 4 in those equations. Where Melissa might pick, anyway, Melissa might pick values for x and y. That when you solve for these, she gets really close to 5 and really close to 1 and really close to 4. So because of that, instead of just having one answer, you're able to look and say, wow, your numbers are really good. His numbers are completely insane. And we do that with models. With over-identified models, we're able to come up with a model that says, wow, the estimates, we try to go back and figure out, based on the correlation matrix, that model sucks. Those numbers aren't even close. But that model has come up with numbers that are really, really close. And that's a better model. So that's the power of over-identified models. It lets you start to evaluate how good of a model, how good that model is, and it lets you start to compare this model versus that model. There's where we get into the argument, which causes which? Well, we can put together different models that start to look at things different theories, which seems to fit better, gives us closer to reality. Exogenous variables, endogenous variables. Exogenous variables are those variables that are the first in the model. Nothing's pointing to them. They're the ultimate cause sort of thing. Nothing predicts them. They predict other things. Endogenous variables are everything else, everything that's being predicted by something else. They all have arrows pointing to them. They may have arrows pointing to other endogenous variables. So you have an exogenous and then a whole bunch of endogenous, and the endogenous's are pointing to other endogenous, but nothing points to the exogenous is that ultimate outcome variable. Ultimate predictor at the very start. Measured and unmeasured, we've talked about this a little bit. The measured variables, that's the ones we have data. Squares, and yes, it's rectangles, yes. In SEM, the measured variables are drawn as rectangles, not circles. I mean, I've cut and pasted. Sloppy, sloppy, sloppy. So measured variables, that's the ones we have data on. They're rectangles. Unmeasured variables, those are like we've just seen with the disturbances, things we don't have data on, but we're estimating. And we'll spend a lot of time outside of residuals, we'll create latent variables, which are combinations of measured variables to make an even better measure as ovals or ellipses. So yeah, measured and unmeasured. Common causes, we talked about this a little bit last week. And the importance of common causes. They're not just factors that predict the outcome or factors that are influencing the variable of interest. It's got to be things that predict both the variable we're really interested in, if we have a key variable we're interested in. Common causes predict the variable we're interested in and the outcome. And that's often for, give kind of the nature, you often see this as an issue when we're interested in things like interventions. That what are the factors that may influence whether you're in the intervention and influence your outcome score. And if you do that, because we saw the direct and indirect effects, you can see the problem if you don't have that common cause. The effect size may look a lot bigger because it's getting credit for whatever that common cause was. Because that common cause isn't there, the effect is, think of the Venn diagram, there's a chunk of its effect that should be carved out and given away to that common cause, and it's not. So it's cheating. It's getting credit for things that it shouldn't be able to do. So for example, intervention, you might have an intervention. If teachers are picking who gets the intervention, they may just go in and may give that intervention to kids that are the most in need. But then things like parent education may be related to the intervention and may be related to the kids' grades because they're giving it to the kids they think are most in need. Or it might be that the other issue we've seen with interventions, school-based interventions, the parents who are most on top of things find out you're putting in a new math curriculum that's really, really great. Get my kid in that classroom. And then it's the opposite effect. Certain kids and families lead to higher higher parent involvement in education lead to higher grades, and it also leads to the kids getting certain interventions. So it's a problem because whatever those common causes are, their effect needs to be taken out of the effect of our intervention, or we're overstating the effect of the intervention. Head Start had problems with this when they first went out, and they were publishing stuff, and people came back, and that was one of the things they quickly did some very simple stuff to point out, well, you've overstated the effect. This is like in the 60s. And they spent decades then kind of wrestling with that. Every time they'd publish, and every time you'd get advocates saying, oh, look, we need to get Head Start, help these kids. Someone would come back and say, yeah, but you guys lie about your effect sizes because you didn't control for stuff. I like Head Start, but that's the problem when you do bad research. So that's why we like randomized control. We talked about this because once you've randomly assigned people into an intervention, and this mathematically or visually is why we like randomized studies. Because once you randomize people into the intervention, there is no common cause. It's all, by randomly assigning kids, you've taken care of all the common causes. We don't talk about it that sense, but that's what we're talking about. Parent education can still have an effect on grades, but it's not a common cause. So it's not going to bias your results for the intervention. Because they're uncorrelated, their circles don't overlap. And there's nothing to take out of the effect of the intervention. That's why we like randomized studies, because it removes, magically almost, removes the effect of all the common causes. Okay, let's start with a simple model. Let's go back.